Today, I would actually like to start with two questions. So if everyone can move over to the polling area in the stage, part of the kind of right side panel, we have posted two questions there, which I would like to start with this morning. So the first question is, have you heard of transfer learning before? So if you can move into the polling area, you can toggle between chat and poll in the stage part of the right-hand side panel, if you can put in your answers there. And I would also like to know if any of you have actually used transfer learning in any of your projects. So I would really appreciate it if you, as the audience, can move to the polling area and input your answers there. So I'll just give it a few more seconds to make sure that everyone is finding the poll. Okay, so I see a lot of answers are coming in. I see that at the moment, like 62% of you have heard of transfer learning. And then of the ones that answered, if you have used it, 94% of you have answered yes, so that's great. My goal for the presentation today is that everyone listening will at least know what transfer learning is. And I hope to also inspire some of you to at least consider using this method in your projects if you find it relevant. So the topic of my talk today is transfer learning physics of multiphase flow. Now I know that's a mouthful, so I'm going to start with explaining what multiphase flow is and what transfer learning is before I move into why we start to explore these methods in Solution Seeker. And after that, I will give you some details about how we actually did it and what our approach was. Okay. So in Solution Seeker, our passion and expertise is on production optimization. I actually did my master's on optimization methods. And the reason why I got interested in this topic in the first place was that I was really intrigued by the possibility of mathematically calculating the optimal solution to a problem. And I've been hooked ever since and been working on these problems for the past 10 years. Also, to say a few words about the impact in this in our industry, everyone believes that we can increase our production by 2 to 5% if we are able to just operate our wells and our assets in a better way without any other investments in infrastructure. So there's a huge gain to be had if we can operate in a better way. Okay, so if you care about production optimization, you care about your producers, which in this case are your wells. And the key question is, how much oil, gas, and water is flowing from each of your wells? And production optimization just means that you want to increase the throughput of something that you care about. In this case, you want to maximize your oil production. Now, in an asset or your kind of factory, you usually have multiple wells. So then you just need to maximize the sum of the production coming from all of your wells. Now, if you are in the offshore industry, usually these wells are placed on the seabed. Their production is routed through a pipeline up to a platform. And on this platform, there is a separator, which basically just is a tank. And this tank, due to gravitational forces, just separates this multi-phase flow and production that's coming in. It separates it into gas, oil, and water, and you get pretty accurate measurements of your total production. So let's say that you have a production engineer at this asset. Let's call her Sarah. The main question still remains for Sarah, and she needs to know how much oil, gas, and water is coming from each of her wells. And that's actually quite a tough question to answer accurately. So that was a few words on multiphase flow and production optimization. I would like to say quickly a few words about the transfer learning concept also, so you know kind of what we're talking about. So transfer learning is storing knowledge learned while solving one problem and applying it to solve a different but related problem. So let me give you an example. If you wanted to learn to recognize cars, you could use a neural network for that. You could go online, sweep the internet, download millions of car images, and probably get a pretty high accuracy on this problem. Now, say you want to do the same thing for trucks. What you're going to find is that there are a lot less images of trucks online, and your accuracy is going to suffer. So then in this case, it turns out that you can actually transfer some knowledge from a car recognition problem to the truck recognition problem and increase your accuracy. And the reason this works is that these problems are related, and intuitively we can think of it that there are some commonalities between cars and trucks. For example, detecting the wheels perhaps, and that knowledge is going to help you get better accuracy on the truck recognition problem. So that was a quick intro to transfer learning. I will come back to how we actually apply this concept into the well modeling problem. Before we do that, I would just like to get into why we started to explore this method in Solution Seeker. So before you start to make something new, it's usually a good idea to check how existing solutions are doing. And that's what I'm showing you in this graph here, which is a cumulative performance plot, where we are showing you average performance from multiple fields and a lot of wells. So what you can see on the x-axis is the deviation or the error from your estimation to the true oil, gas, or water value. And on the y-axis, you have the cumulative performance, or simply put, you can think of it as the amount of time that you can reach a certain deviation. For example, if you want to read off how often you are able to achieve an error of a maximum 10%, you can read it off the graph like I showed you in the slide, and you see that you achieve that only 30% of the time, which quite frankly is not that great. And in Solution Seeker, we started to realize this all the way in the beginning when we started the company, because we wanted to put optimization algorithms on top of these estimations, but we saw that they weren't really good enough in order to do daily and short-term production optimization. So since we are a data-driven company, we decided to use machine learning to explore this problem, and we started to use neural networks. So we did a lot of work on this. We experimented with a lot of different architectural setups and tested a lot of things. And on this slide, I'm showing you the results of a comprehensive study that we did on 60 wells to see what type of performance we could get. We did this about 2 years ago, and I'm showing you the results of that, when we were able to achieve a maximum of 10% error about 70% of the time. Now that's an improvement, but what we realized is that these results were had a high variation among the wells. So even though the average performance looks like it's much better, when we looked at the individual models of the 60 wells, we saw that some were great, but some were not really performing well at all. And just a quick note here, I'm going to compare some different types of models later in the presentation, and I will also include these types of models in that study. So these models, I'm just calling them well models. So just try to remember that when I mention this name again later. Okay, so we wanted to take a deep dive and see why these results were so high in variation. So we dug deeper and we identified 3 main challenges that I'm showing you on the slide now. And I'm sure a lot of you are also experiencing some of this in your own projects, especially the first one. But I would like to focus on the one in the middle here, because we are operating in a small data regime. And to put this into context for you, I'm showing you the number of training points that we had for these 60 wells on the graph on the slide right now. And as you can see, the well with the most amount of data points is reaching perhaps around 5,000 data points. But as you can see, a lot of these wells are clustered around just a few hundred data points. So that is a lot less than hundreds of thousands or millions of data points that you have if you want to do, for example, image recognition. So we are in this low data volume environment. In addition to that, we also have a low data variety environment. And what do I mean by that? For a lot of our explanatory variables, for example, a valve opening usually goes from 0 to 100% opening. What we see is that for a lot of these values on the wells, we see that many of the wells are only covering a small part of that total range. So as you can see, the green and the black well in this slide, they are only covering values between 20 to 40%, while you would hope to have values from 0 to 100. Yeah, so to summarize this, we are in a small data regime, and we see that the wells are very different in terms of the amount of data that they have. And this was the realization that set us on the path to transfer learning. Because if you look at the volume graph again, we started to think that, okay, some wells only have hundreds of data points. Can they actually learn something from the wells that have 5,000 data points? And I just want to also mention that if any of you are experiencing anything like this, it could be a good idea to explore and experiment with transfer learning. The only caveat is that the problems that you're solving need to kind of be a bit related, and some lower level parameters and features need to be it has to make sense that they could be shared, kind of. All right. So let's get into the how we did it. I want to start again with taking a step back and starting with the concept. So what we are actually assuming when we conceptualize this is that we're assuming that there is an underlying physics of well flow that can be captured given enough data samples. And what we are then saying is basically that knowledge about one well can help us predict the behavior of another well. And I just want to take a step back again here to just state that this is actually quite a radical idea. Because if you ask subject matter experts about this, they are probably going to say that this is not going to work because each well is so unique and reservoirs are so unique and different between assets that there is really no commonalities and possibilities of learning across. And I have to say that risk is real. And when we started to think about this, we were kind of worried that you might actually do worse if the wells are so unique that you can't learn across. So we were thinking that the risk of predicting worse on a well by bringing in data from another well was definitely there. But nonetheless, we were really excited when we got this idea and wanted to try it out anyway. So we started to combine data and combine parameters in the architecture. So we started with some just exploratory analysis. And we started to use, for example, principal component analysis just to visualize and see if there are any patterns. So that's what I'm showing you in this figure, where we have done, or I'm showing you the two first principal components of the data set with the 60 wells. They are colored according to the asset that they belong to. And we were super encouraged when we were able to create this figure, because we see that the points are lining up quite nicely and in a way that kind of makes physical sense. And the way you could interpret this is if you wanted to model one of the wells from the green asset, it kind of makes intuitive sense to think that you could interpolate between the blue and the purple points. So this just really encouraged us and made us believe that there are commonalities and there are possibilities of learning across wells, assets, regions, and around the world. Okay, so another quick step back in case I'm getting a bit far out there. We are still trying to help Sarah figure out how much oil, gas, and water is flowing from each of her wells. So then we did a big transfer learning study on 55 wells, this time from 4 different assets. And we created 3 different models to compare the performance. The first models are these well models that I introduced to you earlier. These are models that are taking data from just one well and then modeling and predicting the behavior of just that well. So you end up with 55 kind of isolated well models. Then we created 4 asset models, and that means that we took all the wells belonging to one asset And the data from there, we combined that into one big network. And then the output was the oil, gas, and water predictions on each of those wells at the same time. And so, for instance, if you on one asset have 10 wells, you would put the data from the 10 wells into this model, and so on. And finally, we made a universal model, which takes data from all of the 55 wells, puts it into one huge transfer learning or multitask learning network, and you get the oil, gas, and water rates for all 55 wells out at the same time. So now I would also like to ask you, the audience, another question before I move on. So I would like to know which one of these models you think is going to have the best performance. So please move over to the polling area of the stage panel and then put in your answer. Okay, just 2 votes. Please move to the polling area. I think it's kind of fun to see what you as the audience think is going to have the best performance. I will give it a few more seconds, so please move over to the polling area. Let's see what you think is going to have the best performance. Okay, a lot of votes coming in. I'll give it a few more seconds. The poll is up, the question is up in the polling area of the stage panel. Okay, so we have a lot of answers coming in now, so I'll give it a bit more time. It's fun to have kind of a cliffhanger, I think, in the presentation. Okay, a lot more votes coming in now. All right, so it looks like most of the ones that have guessed, 52% of you are thinking the asset models will do best. 30% think the universal model, and 17% think that the well models will be the best. So let's take a look at the results. So these are the results of this study. On the y-axis this time, you see the error or the deviation. And on the x-axis, we have plotted weeks since training, because in addition to just looking at the error, we wanted to see how these models perform over time. And then the blue, again, are the well models. The green boxes are the asset models, and the orange are the universal models. So what you can actually see here is that the models are quite similar on average. So there's not a huge difference between them. But we also see that they deteriorate a bit over time. So you see the error is moving up a bit as you move away in time. We also noticed that the transfer learning models, the green and the orange, they are adding some robustness far into the future. So in week 18, you see, for example, that the orange model is performing significantly better than the other ones. And then to speak to the question I posed, we see that the asset models or the green models are slightly better than the other ones in most cases. So good job for those of you who guessed the green models. And that actually makes kind of intuitive sense too, because you would think that the wells that belong to the same asset actually have more in common and have more to learn from each other. But the final conclusion for us, which was super exciting and very encouraging, is that we noticed that sharing the parameters does not actually degrade performance that much. So that means that there is really no real downside to sharing data and sharing a lot of the parameters in the network, which is great. So obviously, this is something that we are continuously moving on, and we still have a lot of research questions and really exciting questions to answer, but it's really encouraging to see these results and see that there is no downside in sharing. And I really believe that this type of results is going to be a game changer for this oil, gas, and water estimation problem. Okay, so I have one final point I would like to make, which is, in my opinion, the greatest part or the greatest learning that we had. So let me explain it with this graph. So we see that the transfer learning is actually letting us learn the physics. So let's get into it. Here I'm showing you the relationship between one of the inputs to the model, which is the pressure, to the output of the model, which is the oil, gas, or water flow. And then you see the black points in the graph in the middle. That's the real data that we had. And as I mentioned earlier, we have this low variety data. So you see that we are not covering a big range of data for pressure, as you can see. So what we wanted to do was to sensitivity check these models and see how they performed if we actually changed one of the inputs. So what we did is that we fixed everything else in the model, but we changed the input pressure in a range from 50 to 70, just to see how the models would behave and predict the change in behavior on the well. And the blue lines are the well models, and the orange lines are the universal models. And what you can see is that the blue models are actually predicting a counter-physical behavior. That means that it's predicting that the flow will decrease as you're increasing your pressure, which in most cases doesn't really make physical sense. If you increase pressure, you would expect an increasing flow. But what you can see on the universal model or the transfer learning model is that that model is capturing this physical behavior in a beautiful way. It's nonlinear, it's increasing. And Sarah, the engineer, would be super excited to see these models, and that would increase her belief in these models. Just want to emphasize that this is actually the key to be able to do production optimization, because it's not enough to just historically estimate and match what these rates would have been. We need to be able to predict how the flow will change in the future if Sarah changes one of her controls. That is the answer that Sarah needs to get from our models. All right, so that was basically the content of my presentation. So just to summarize, transfer learning is storing knowledge while solving one problem and applying it to solve a different but related problem. And if you have a small data set and you find a related problem with more data, it really makes sense to try and explore this transfer learning or multitask learning types of architectures. I also just want to thank our research lab for outstanding work. It's really their hard work and ideas that I presented to you today. Also just want to say, if you have any more questions or comments about my presentation today, please get in touch. Add me on LinkedIn or shoot me an email, Sheri@solutionseeker.no. Also just want to mention that Solution Seeker has a breakout session in about a half hour, 40 minutes. Please join us. We will showcase many of our other amazing women at Solution Seeker. So thank you so much for your attention.